Welcome back to section 2 of chapter 3. In this section, we're going to be looking at exponential and logistic modeling. So we just looked at their equations. So now modeling, getting the real world data and making a mathematical model to match the data. So our learning targets today, we're going to identify and analyze exponential growth and decay functions. We're going to determine exponential functions that satisfy given conditions, determine logistic functions that satisfy given conditions, solve applications involving exponential and logistic modeling, and then describe and compare characteristics of exponential, logistic, and other models. So, first of all, let's look at exponential models. This, like the last one, the exponential models are the bigger of the topics. So when we have an exponential population model, it doesn't even have to be a population model, but it's just using population. It's just any percent change, really. The model is P of t equals P naught, which is the initial value, and then R, which is expressed as a decimal, and T is time. In years, it's actually just whatever the time increment happens to be, but for populations, it's in years. So if we're looking at something, say like P of t equals 85723 times 1.075 to the t, what that says is the initial population was 85,723, and we're growing at a rate of 7.5%. We could also have something like P of t equals, gonna say 10,000. We'll keep it as a base number for that initial population times 0.997 to the t. So the initial population was 10,000, and here the rate, it's 1 plus something. Well, we're at negative 0.003, so that'd be negative 0.3% growth. So that would be a exponential decay as opposed to an exponential growth. You're always losing stuff. Now, notice the percents when they go into the equation go in as a decimal. You do have to move that decimal place over twice. That's one of the big mistakes people make when they're doing these. So if we wanted something with, let's say the initial population was 57,572,341, and it's growing at 2.1%, we could make an equation. That's just P of t equals this population, 572,341, times 2.1% is 0.021, so that'll be 1.021 to the t. So we can make the equations, we can look at the equations and just pull out those values that are important, that initial value and the rate of growth or decay. Growth and decay. That growth is when the rate is positive. So when you're looking, that base has to be greater than 1. Decay is negative, so that base would be less than 1. Just like we saw, like the 0.997 is less than 1. The 1.075 and the 1.021 were both greater than 1. Growth looks like that, and decay looks like that. They both have an asymptote going to 0, and it's just getting there. It's either going away growing or it's getting closer to zero. We have radioactive decay as well. Now, radioactive decay is dealing with like a half-life. And what half-lives are, and we'll see this more later on in the chapter, but what half-lives are is for every time period, you get half of something. So, for instance, if we have a certain radioactive substance has a half-life of 20 days, and its mass was 5 grams initially, that means at time 0, we have 5 grams. At time t equals 20, we have half of that, so we'd have 2.5 grams. At time t equals 40, we'd have half of that, so we'd have 1.25 grams. And so we're always, every 20 days, we just have half of whatever we had at the beginning of that 20 days. So we could write an equation. We have the amount, so let's say A of t equals our initial amount, 5, times 1 minus 1/2, so it's just 1/2, to the t, but it's not just to the t, it's the t over 20 because the half-life is 20 days. And here t will be measured in days because that's what we're measuring in this problem. If the half-life was 20 years, the problem would be, or the equation would be identical, but t would be measured in years. Same thing if half-life was 20 minutes. It would be the same, but t would be in minutes. And so, but we have that divided by 20 because of that 20 days. So every 20 days, we're going to multiply by another 1/2. And so it's asking, when will there be 1? Well, it'll be after 40, but probably before 60. Because when we go half of 1.25, we're going to get 0.6. It's 0.625. So it'll be in between there somewhere. But we can't tell. We don't want to keep guessing and checking. So later on in the chapter, we will be seeing how to do this analytically, which is algebraically. Right now, though, we can do it graphically. And so we can graph this equation that we just made, and we can graph y equals 1. We get something that looks like this, and we're looking right here for where they intersect. And I just wrote on it and kind of covered it up a little bit. But it looks like they intersect at about, let's see, it's before 50, looks like about 46 or 47. So t will be about 46 days. And we could plug that in. We can go 46 divided by 20, 1/2 to that, times 5, and see if we're close. So this gets us a guess. We could plug it in to make sure our guess is right. And it's like, all right, well, it's still a little bit above, so maybe try 47. All right, that's about right, or a little bit below. Maybe it's right in the middle somewhere. You're not going to get it perfectly, but it's going to be about 46 days-ish. Using regression. So that was something that's happening in a natural way, and it's going to keep being normal. A lot of things don't fit perfectly like that. A lot of things, the data it's not going to be a perfect exponential, but we can still make an exponential model to fit it. For instance, population. Here we have the US population in millions from 1900 up through 2016. This is complements of the census. Notice it happens we have data every 10 years. We can graph this, and we'll see a graph here in a second, and we'll see it has a nice little exponential curve to it. So we can do our regression a couple different ways. We can use our calculators. If you have a calculator handy, you do this regression the same as you would do any other regression. You're going to enter your data, in the Stat and Edit menu, and then you go to Stat Calc, and we can pick Exponential Regression, or you can also pick Logistic Regression. That's the other one that we're looking at in this section. And then it's still going to ask for your X list and your Y list. You put it in, everything's the same, and when you do regression in these calculators, except for which regression do you pick? What kind of model do you want? So you can do that, and then you hit enter, and it gives you your answer the same as it always has. Or we can do regression in Desmos. I think I've probably mentioned that I really like how Desmos does regression. It is so so slick. It's really quite wonderful, and everyone has access to it. Everyone doesn't have a calculator. So when you go to Desmos and you just go to the graphing calculator part, you can enter a table. To get the table, you hit that plus sign right there, and it'll give you a few options. One of them is a table. So a table, it labels it X1, Y1, and then you just fill in your table just straight from the data. Now notice I actually didn't go straight from the data. I have 0, 10, 20. This is years since 1900. A lot of times when we're dealing with data, specifically year data like this, we don't want to go down to year 0 because the US population in year 0 is, well, there wasn't a US. I mean, there was a North America and it had a population, but we have no data on that, and things changed so much that it wouldn't fit the same model probably. If you start out with year 0, this goes into the exponent part, and that is very, very touchy. So even a small little like rounding error, like 7 or 8 digits down, is going to seriously affect your model by the time you get up to 1900. So when you're dealing with years like this, you always, always, always want to scale it. So you get your data entered, and then for regression, you just type in the equation you want it to be used for regression. So here for the exponential, it's y1 a tilde, which is the second button, and then it's like right to the left of the 1, or shift, then right to the left of the 1, a times b to the x1. Now, for y1, like there's a little subscript. I didn't enter a subscript. I just typed in y1. It put the subscript there. Then a tilde, a times. The times is just the shift 8 to get the little star, and it puts it there as a multiplication even instead of a little star. B, and then use the caret button, which is shift 6, and then x1, and it again put that 1 in the subscript of the x, and it gave us the equation. What's really fun with these is if I type that in first and then I start putting the data in, I could see how each data point would affect my line. So that's the exponential regression, and then it gives you your equation down here the same as the calculator would. It gives you what A equals, what B equals. I also did a logistic equation. A logistic equation is like that. Remember the equation, y equals a over 1 plus b e to the negative cx. And then it gives us a, b, and c. So that's how you do a logistic. You just type in the equation. If you want linear, you type y1 a tilde m x1 plus b. It's whatever you want. And so looking at these two graphs, they both hit it fairly well. So now the question is, what will the population be in 2020 or 2050 or 2100? What would the population be? What model would we want to use? Is the population going to keep growing exponentially? Or is it going to hit a logistic curve? So if we zoom out on this graph, I zoomed out, so now like this is kind of where the window was. We zoom out, we have the exponential curve is going to keep rising exponentially. So this says in, let's see, 150 would be 1950. We'd be at like 500 million, and 2100 we'd be up at like 900 million. I think they were millions. We'd be up at 900 million, and it grows crazily. That's what an exponential growth is. The logistic, it grows, but then it kind of tapers out because it has this asymptote that's getting closer to that carrying capacity for the population, which would make a better prediction for years down the road. Is it going to keep being exponential, or is it going to level out and be a logistic curve? You can look at how the two graphs match the points here. The logistics seems to match just a little bit better, but that doesn't necessarily mean a ton. We just have to think like in a logical sense, what would happen later on. Chances are we're going to hit a population carrying capacity, but as technology increases, that carrying capacity also grows. So I think it'll probably be somewhere in between these two models. Anyway, that's what the type of stuff we're doing today. You're looking at exponential and logistic models, um, a little bit of regression, writing, analyzing these models, and then when we're solving, use a graph and find the intersection points. So I will see you in class, but until then, keep working problems, keep asking questions, and as always, happy mathing.